Hello, and in this video we're going to look at asymptotes. In this specific one we're going to be looking at vertical asymptotes. This is part of your handout that I cut and pasted onto this document. It says that asymptote is a line that a branch of the graph approaches. Graphs of rational functions may have vertical, horizontal, and/or oblique slant asymptotes. For each rational function graph below, write the equations of the asymptotes. So if you're looking at this equation right here, this one looks like it goes through y equals 1. And then this one's x equals 2. And this is x equals negative 2 on this one. So it has two vertical and a horizontal. Now this one has an oblique asymptote and a vertical asymptote. You can see that it has this vertical asymptote. It's not drawn in here, but it doesn't cross the x-axis or the y-axis, so that's going to be x equals 0 for that asymptote. And this one we just need to know what the slope is. It looks like it goes through 1, negative 1, and negative 1, 1, so that means the slope is rise would be negative 1, run is 1, so this has a slope of negative 1, so that means your answer here for your asymptote is y equals negative 1x, because it goes through 0, 0, so it's plus b, which is 0 here. So y equals negative x is our asymptote. In this case, an oblique slant asymptote. So in this video, we're going to look at vertical asymptotes and how we find it from the actual equation. So from our actual equation, we find vertical asymptotes when we first write the function in lowest terms, and we have to find out where the x values of the function are undefined. So usually what we're going to be looking at here is when is the denominator equal to 0, because then that's going to mean that the function's undefined. So we're just looking at mainly our denominator. We're going to look to see if it's been factored and reduced here. So in my first example, g of x here, we can't factor anything in the numerator. We could factor the denominator, and we're going to do that, and actually to find out where our undefined values are, we're going to just look at our denominator, x minus 4, and or x squared minus 4. We're going to set that equal to 0 and find our solutions. Now this factors into x minus 2 and x plus 2 equals 0. So that means that our answers here are x minus 2 equals 0, x minus 2 equals 0, or x plus 2 equals 0. So that means x is 2 or negative 2. Those are actually where they're undefined. So that's where our asymptotes are going to be, at 2 and negative 2. So these are going to be our asymptotes for this function, x equals 2 and x equals negative 2. Because we found out where it was undefined. It was undefined at this point because that makes the denominator 0. Now let's look at my second example here. In my second example, it's been reduced as much as possible. Our denominator is x squared plus 1. We set that equal to 0. This doesn't factor because it's a plus 1, but if we try to solve it by using the square root function, we could do that as well up here. We'd have no solutions here, no real solutions to this equation. We can't have something squared equaling a negative number, so that means that there are no vertical asymptotes here. There's no vertical asymptotes because there's no solution to this equation. Alright, and now we're going to look at this one as my last example. Now both these can be factored, so I need to make sure I do factor these to see if we have to check for a reduction, because it says here up here we have to have the function in lowest terms. So the function has to be in lowest terms before we look at the denominator. So I need to factor these both. Up to this point I didn't have any to factor, but in this case both the numerator, x minus 3 and x plus 3, for that one, it factors into this. This one we want to find factors that multiply together to give you negative 21, but they have to add to 4. Alright, so one was negative, so 7 and 3 are 4 apart, so one of these has to be negative. It would be this one, 7 minus 3 equals 4. So this would be positive 7 and minus 3, negative 3. Now, since I did factor this, this actually reduces, so we need to reduce these terms before we move on to finding asymptotes. So to do that, we reduce these terms, so it reduces to this term here over x plus 7. So this is the only place we look for an asymptote. So x plus 7 equals 0, because that's where it's undefined. So x equals negative 7 is our only asymptote. In actuality, this minus 3 is still going to have a non-defining effect on our domain. So our domain is still going to be our domain for this function. It's still going to be all real numbers except a negative 7 and positive 3. Oops, positive 3. Because of this, of these two factors in the denominator. But what really happens at this positive 3 value is that we get a little hole in the graph, and we can probably see that if we look at this graphing calculator. We might be able to see that little hole. Let's see if we can do that. See if we can graph this and see the little hole. Now this is it's going to be very small hole, so we have to make sure that we have it set up correctly so that it's we have to have it kind of zoomed in so that the factors of the each one of the pixels on the screen is translated into a it's not rough graph. It's got to be a smooth graph here so that the pixels will pick up the hole that's missing. So we're going to try this. 4x minus 21. We're going to look at this. Now, it has an asymptote at negative 7, so we're going to do a little zoom here, and we're going to do our square decimals, 4. We're looking for the hole at 3. So we can kind of see it right here. We look at the graph right here. Right here, see that little space right there? And if we did a trace on this function, and we went to the right, since it's going up by tenths, we could see that at 3 there isn't a spot. There's a hole there. But anything in between that, there is values. Now we don't see the vertical asymptote at negative 7 because I zoomed in on this, so my window is very small. If we want to zoom back out for a standard window, 6, we can see the asymptote right here. And the calculator tries to connect here, so in that process you can kind of see where the asymptote might be. If you were drawing this on your paper, you wouldn't draw this line connecting them though. And you can't really tell where the missing hole is because we zoomed out so far we can't see that hole that's missing. So that's looking at the graphing calculator in this problem.